Hey guys, I'm Prabhdeep Dhillon. In this lesson we are going to cover the second section on higher order linear equations. We are going to be looking at homogeneous equations with constant coefficients. So let's just start off by looking at the nth order linear homogeneous differential equation. To solve these problems we are still going to be finding suitable values of r, and we can do that by setting y equal to e to the power of rt. We'll go into more information about the characteristic polynomial going up. Uh, there are still three main cases in these types of problems. Problems with real distinct solutions, problems with repeated roots, and problems with complex roots. You'll now learn that these can be repeated as well. In second order differential equations, each differential equation could only involve one type of these cases. But now that's, however, not necessarily the case. We could very easily have differential equations that contain each of these cases. So the characteristic polynomial is the polynomial ZR specifically is called the characteristic polynomial. When ZR is equal to 0, it becomes the characteristic equation for that differential equation. A polynomial of degree n has n zeros. So this allows for this equation to be written like this, and they're still equal to each other, and they're both ways to display the characteristic polynomial. So we will be talking about roots of these characteristic equations. There are three main types: real and unequal roots. Uh, those are pretty straightforward. They're real numbers, and they're unique, they're not equal to each other. Complex roots, so we'll be dealing with complex numbers in those, and repeated roots. With a polynomial with n degrees, it is possible that there are many zeros that are equal to each other, and so that allows for a lot of possibilities with these higher order differential equations. So we'll go into more detail about real and unequal roots first. When there are real roots, when the roots are real values and none of them are matching, we end up with as many distinct solutions as we have degrees. So if there are 5 degrees, there are 5 distinct solutions, and if for n degrees, there are n distinct solutions. When the function is linearly independent, we can write it in the general solution form. So this right here is the general solution form. And so how do you make sure that the function is linearly independent? One of these ways you can do it is by solving the function and evaluating it for its Wronskian determinant. With the real and unequal roots, the characteristic equation, the general solution of the characteristic equation is just a sum of the exponential functions. So if you look at it again, you'll just see that it's adding up the exponential functions. So just some more things to note. When the value of t gets larger, we will see that the largest root will have more and more impact on the solution. So say the largest root's a really large positive value, uh, the function will grow exponentially. And if the root's a very large negative value, you're going to see that it's going to move very quickly towards 0. This will result in the solution becoming exponentially bounded or moving it exponentially to 0. So now let's take a look at complex roots. Sometimes the characteristic equation will have complex roots. These are going to exist in this conjugate pair always. They're not going to show up in other forms. Uh, this is because the coefficients for the characteristic polynomial are always going to be real number values. So you're not just going to get a random I or something. In order to get real valued solutions, we are going to replace the complex valued solutions with these real valued solutions here. This is the same thing that we did for second order equations, and this allows us to express the solution with real values even if there are complex roots in the problem. Now we're going to be taking a look at repeated roots. When we deal with the scenario where the roots of the characteristic equation are no longer unique, we're dealing with repeated roots. Let's start off by looking at how this applies to real roots. Say the root of the characteristic equation is equal to 0. Say we have a root R1. The nth order equation has a multiplicity s, and this is what the repeated roots are going to be replaced with. So e to the r1t, t e to the r1t, t squared e to the r1t, for however many times that root shows up, however many times it's repeated, we're going to continue with this trend over here. We will end up doing the same thing to repeated conjugate roots, and they're going to be replaced in a very similar way. The complex root and its conjugate, they're both going to be repeated the same number of times, and the corresponding real value solutions, you'll see the trend they follow is very similar to how real roots react. So you have this, then you get the t in front of it, and then it goes until you get t to the s minus 1, and you see that's true for its conjugate as well. Computing higher end roots can be done more conveniently using Euler's formula. It allows us to find roots even if they might possibly be complex numbers. It just makes the process easier to do. Here's Euler's formula. Oof. And here is a picture showing, a description of Euler's formula geometrically. So let's take a look at some examples to help us understand what we have just talked about. Find the general solution for this problem. That's going to be our first problem. If you're doing this to learn, it's probably better that you pause now. So try the problem first before going towards solution. So in this problem, we are just finding the general solution. We are going to assume that y equals e to the power of rt, and then determine the values of r by solving for the polynomial equation. We factor 2 to the power of 2r to the power of 2 in this section of the equation. And we factor 2 out from this section of the equation so that we are left with r minus 2 on both sides. This helps us factor it out pretty easily. It's just factoring. We see that r is equal to 2, that r squared is equal to 1, and that means r is equal to plus or minus 1. So the general solution for this problem is listed right here. For our second example, let's try to solve this initial value problem. This is our problem, and right below it is listed the initial values that we will be working with. Here we're dealing with an initial value problem. Again, we start off by assuming y is equal to e to the power of rt. So the first step we're going to take here is we're going to factor this out. And we can just pop an r out here. It's pretty simple. You factor it and you find that the three roots you're working with are 0, I, positive and negative I. So we're going to be dealing with complex roots in this problem. And because we're dealing with complex roots, we're going to have to replace the complex valued solutions with the real valued solutions. This is why we are now using the cosine t and the sine t here. So after replacing the complex valued solutions with real valued solutions, we have solved for the general equation. Using the initial conditions we were given at the start of the problem, now we can solve for the coefficients in this problem. And so we start off with y0 is equal to 0. And we can't really tell anything right now because the only thing we've gotten rid of is the C3 because sine 0 is equal to 0. For y prime 0 equal to 1, we take the derivative of the general solution. And so we can get rid of the constant 2 sine t, because again, sine 0 equals 0. And we find that constant 3 is equal to 1. And the next step we take is for y double prime, the second derivative of y equal to 0, which is equal to 2. So we have negative constant 2 cosine t and then negative 3 constant. We already know this is a 1, we don't need to do anything. Plus, we know sine t of 0 is equal to 0. And so we're left finding out that constant 2 is equal to negative 2. This helps us go back to here and solve for C1. And then we see C1 is equal to 2. Using the initial conditions, we have now solved this problem because we have solved for the values of these coefficients. For our third example, we are going to find the general solution for this problem. For this problem, we are just we're going to be solving the general equation for this higher order equation. For the given equation, we're just going to start off, like always, writing the characteristic equation. When we start factoring out the characteristic equation, we see something funny. We see a bunch of matching pairs. So we end up with this little deal right here. So we see there are two roots for this problem, but each of those roots was repeated 3 times. So we're dealing with a nice little repeated roots problem. So now we replace this equation with these corresponding solutions, because then this is how we solve for the repeated roots. And this is how we find the general solution for a problem with repeated roots. Now that we have solved some examples, I hope you feel more comfortable dealing with higher order differential equations. Once you have an idea of how to work on these type of problems, we realize that working through them is pretty similar from one problem to another. Higher order equations just require patience when working on solving for the characteristic polynomial and for the system of coefficients for the solution. I hope this lesson has been helpful to you to understand homogeneous equations with constant coefficients. I hope you now see the theories that we discussed when we were solving second order linear differential equations and how they extend to higher order linear systems. Again, thank you so much. Hope you have a wonderful time.